This gentleman discovered 200 years ago that in an electric circuit of two different metals, a voltage is created when there is a temperature difference between the two connections of the metal rod. Materials with high electrical conductivity and low terminal conductivity are suitable for these elements, which are named after the discoverer. Unfortunately, good conductors of electricity are also good conductors of heat. The best efficiency is achieved with semiconductors. These are electronic components that are available to us today. Now, the power of a single component is relatively small. However, a large number of these components connected together, i.e. connected in series and parallel as is common in electrical engineering, generate a considerable amount of power. There are various technologies that can convert heat into electricity in one way or another. Steam turbines, ORC, organic Rankine cycle plants, a kind of steam engine for lower temperatures, or the Stirling engine. What they all have in common is that they rely on kinetic energy, which drives the generator to produce electricity. This means that they are subject to wear and require maintenance. The thermoelectric generator produces electricity without these diversions. It contains no moving parts, is maintenance-free, and has a service life of decades. All these technologies that convert electricity from heat have one thing in common: they require a temperature gradient. This means that a source with a high temperature level requires a sink with a much lower temperature. For the thermoelectric generators, this means that its output depends on the differential temperature. With each Kelvin grad, its power increases. On the picture of the calculation application of the thermoelectric generator, you can see the dependence on the temperature. An identically constructed device would generate a current of 400 watts at a differential temperature of 109 Kelvin, as seen in the picture on the left. At a differential temperature of 170 Kelvin, a current of 1000 watts, to be seen on the right picture. Where do we get the heat we need? It does not have to be produced separately, it's already available as unused process heat in industry or as unavoidable waste heat from the operation of power machines. The amounts of energy are enormous. In Germany it's about 814 tetajoules per year. This corresponds to an output of 226 terawatt hours annual. Of this, about 38 terawatt hours are at a temperature level that is suitable for generating electricity with the previously mentioned technologies. Even we were to convert only 5% of that into electricity, that would be 1.9 billion kilowatt hours. That is about as much as the inhabitants of a city like Cologne consume per year. Here is an example of a possible temperature curve when integrating electroterminal generators. We have one heat exchanger on the source side and one on the sink side. In between, a series of cascaded generators. From the source side in this example, we feed in energy with a temperature of 200 degrees Celsius using the medium hot water or terminal oil, and a temperature of 180 degrees Celsius back. On the sink side, the temperatures are 15 degrees Celsius for the feed and 35 degrees Celsius for the return. This gives a mean temperature of 190 degrees Celsius on the hot side and 25 degrees Celsius on the cold side. The effective temperature difference in the generator which determines its output is 165 Kelvin. In a simplified view of the energy curve, without taking radiation losses into account, we supply thermal energy of 180 kilowatts in the bypass, convert 10 kilowatts into electrical energy in the generator, and dissipate the remaining thermal energy of 170 kilowatts via the temperature increase of the heat sink. Let us now look at a possible cause of integration into a cross-sectional technology. The example shows a sewage treatment plant application. The sewage gas coming from the digestion tower is burned by the gas engine and converted into kinetic energy, which drives the generator that produces electricity. It succeeds in doing this with about 40% of the supplied energy. The engine must be cooled, and about 22% of the energy input is used as heat energy for heating water, hot water and sewage sludge heating. The remaining 38% escapes with the exhaust gas into the atmosphere, were it not for a heat exchanger that extracts 20.5% of the terminal energy from the exhaust gas at a high temperature level. This is then fed into the thermoelectric generator, which converts about 5.6% of the energy into electricity. The remaining thermal energy is not lost. It is used further by preheating the sewage sludge. All the electricity is not fed into the public grid, but used in the sewage treatment plant itself. Our development is a realistic contribution to the effort to conserve resources worldwide.